you have to write your roll number, student IDs in the chat box once again, because I couldn't save the previous chat. And I'm going to discuss the problem whose question I wrote in the previous session. So the question was, I'm not going to write the entire question because the question is there in the Friedberg book, Friedberg, section 1.5, question number 8, and we are supposed to check that we are given a set S whose elements are these are the elements of the set capital S, and you know very well that this set is the subset of actually it is a subset of R3, the three-dimensional space, 3D space. Now in the question it is given that we are to check whether this set is LD or LI. This is the first check, and according to the question they have considered this set over the field F, but you know that capital F, if it is given the name R, then the space becomes R3, and R3 is the vector space over R. R3 is the vector space over, is a vector space since Fnf is a vector space. This you know very well. So we are going to check whether this set is LD or this set is Li. In my previous class, we have discussed that any three-dimensional point x, y, z can be expressed as linear combination, can be expressed as a linear combination of elements of S. Okay, so we know this. Now to check whether this particular set is Li, we have to consider these elements individually, and for each of these elements we have to associate some scalars A, B, C. Okay, and we are going to check whether if the linear combination of these elements gives the zero vector, then whether if you have gone through my YouTube video which I published last week, there I showed that if this linear combination is zero, implies that not all scalars are zero, then this means the vectors under consideration are Li. And if this particular linear combination, it implies that all these individual scalars are zero, then that means, sorry, not all scalars are zero, then this means that the vectors are LD. And if individual scalars are zero, then that means the vectors are Li. So we are going to check that this set becomes actually it becomes Li if we consider this field set of real numbers. So let us check it first of all. So now since we have this, so I'm writing directly from this particular step. So if I consider this linear combination to be zero, then we are going to apply the scalar multiplication first of all, the coordinate wise scalar multiplication as discussed in the first chapter. And this is equal to 0, and after then we can apply the coordinate wise vector addition. So it becomes a plus b, this becomes a plus b plus 0 actually. Then the second one is a plus c, you can check it very well, and the third one is b plus c, and that becomes 0 0 0 0 0 0 0 is the vector space of 0 0 0 is the 0 vector of the vector space R3. Okay, now if I compare the individual coordinates from both sides, comparing the coordinates, we get a plus b is equal to 0, a plus c is equal to 0, b plus c is equal to 0. These three equations are coming. So we can name these equations 1, 2, and 3. So you are going to solve these equations first of all. So you can add all the equations together. If I add equations, if we add equations 1, 2, and 3, we get twice a plus b plus c is equal to 0. This is my equation. You can name this equation as equation 4. Now from this equation I am going to subtract my equation a plus, say what equations I have. We have b plus c. So let us subtract b plus c. Let's see what happens. So we are going to subtract this equation b plus c, which is actually, according to my writings, it is actually equation number 3. So if I do so, we are going to get actually not, I'm multiplying equation 3 by 2 actually, then okay. So if I do so, then we can find that this is equal to, this becomes twice a equal to 0, and this implies a is equal to 0. Okay, so the first scalar has come out to be 0. If I substitute this value, because we have other equations with a plus b equal to 0 and a plus c equal to 0. So after substituting the value a is equal to 0 in equation 1 and 2, in equations 1 and 2, we get b equal to 0 and c equal to 0. And by the property of, by the definition of linear independence, we see that the vectors 1, 1, 0, 1, 0, 1, and 0, 1, 1 are linearly independent vectors, are linearly independent or Li vectors, linearly independent or Li vectors. Okay, so first part is done. Next, in the next question, what was given in the question? In the question, it was given that if f is the field which is of characteristic 2, so the part B gives you this particular assumption. In part B is that f is a field of characteristic 2. F is a field of characteristic 2. And we already know that such an f can be represented by Z2, where Z2 has got two elements, 0 and 1. So 0, 1 is a field with respect to the operations. I'm again writing it 1 plus 1 equal to 0, 1 plus 0 equal to 1, 0 plus 1 equals to 1, and 0 plus 0 equals to 0. And with respect to multiplication operation, we have these operations, and okay, so with respect to these operations, F is a field of characteristic 2. So I'm going to check if I consider the vector space V over the field Z2. If I consider the vector space now over the field, if we consider the vector space V over the field Z2, V over Z2, then whether the set S is Li or Ld, whether the set S is Li or Ld. Okay, so we are still considering our vector V to be F3, our vector space V to be F3, but instead of taking the field as set of real numbers, we are considering it to be the set of set which is denoted by Z2, that is a finite field is considered. So we are going to check whether under this condition our set capital S is Li or Ld. So just as before, we are going to assume three scalars. We take three scalars, A1, A2, and A3, such that A1 into 1, 1, 0 plus A2 into 1, 0, 1 plus A3 into 0, 1, 1 is equal to 0, 0, 0. This implies A1, A1, 0 plus A2, 0, A2 plus 0, A3, A3, 0, 0, 0. This implies A1 plus A2, A1 plus A3, A2 plus A3 is equal to 0, 0, and 0. Now you see, if I compare the coordinates, we get A1 plus A2 is equal to 0, A1 plus A3 equal to 0, and A2 plus A3 equal to 0. These are the first three equations which I have got from the equation, the linear combination we have considered. I am going to subtract equation 2 from equation 1. Okay, and what we get if I do so, A1 plus A2 minus A1 plus A3. Okay, if I do so, you get this, which implies A2 minus A3 is equal to 0. This is my equation 4. And if I consider equation 3 and equation 4 together, and if I add equation 3 to equation 4, what do I get? We get twice A2 is equal to 0. Twice A2 equal to 0. Now you see, we know that Z2, the characteristic of Z2 is, the Z2 is having the characteristic 2. What does it mean? For all x, x plus x becomes 0 actually. Okay, here if you apply this rule, if we apply this definition of characteristic over here, you see Z2 has two elements. So here the possible values of X are 0 and 1. So you get 0 plus 0 equal to 0, and 1 plus 1 is also equal to 0. Okay. So with this, we can write it as, we can consider this to be A2 plus A2 equal to 0. Why? Because now since A2 and since AI has been chosen from Z2, AI has two choices only. Remember this, two choices only. AI can be 0 or 1 for all I. Okay, so therefore, now you cannot say that since 2 is not equal to 0, since 2 is a non-zero number, so the other element must be equal to 0 so that the product is 0. That is not the case for Z2. For Z2, we can get the result 0 only when we add the element twice with itself. So A2 plus A2 is actually becoming 0. Okay. So that means what? That means A2 is not equal to 0. Individual element may not be 0. Okay. So since for Z2, if we consider A2 to be 1, then 1 plus 1 is 0, but A2 is not equal to 0. Okay. So I'm explaining this thing in the next page. For example, if we select A2 is equal to 1, then A2 plus A2 is equal to 0, but A2 not equal to 0. If we select A2 equals to 0, then we can say that A2 equal to 0, and as well as A2 plus A2 is also equal to 0. But this is only with this case when A2 equal to 0, but A2 can have other values, and the other value is 1. So for 1, we cannot say that A2 is 0. And therefore, if we proceed in a similar manner, by proceeding in a similar logic, we see that the scalars A1 and A3 have also two choices, and depending on the choice, they may or may not be 0. So not all scalars AI I is equal to 1, 2, 3 are 0. Hence, S is linearly dependent when the field is Z2. Okay, so this is the problem which I wanted to discuss. This is a very important problem. This problem is very important problem. Now we can consider another problem, which is problem number 11 from the book, from the section 1.5 of Friedberg. The question number 11 says, let me write the question. Yeah, the question says that let capital S is equal to U1, U2, UN be a linearly independent subset, be a linearly independent, linearly independent subset of a vector space V, of a vector space V over the field Z2. How many vectors are there? How many vectors are there in span of S? Justify your answer. Justify your answer. So give an example of three linearly dependent vectors in R3 such that none of the three is a multiple of another. Any idea? Have you understood this problem? How this particular result has become 2 to the power n? It's because this particular vectors in the set capital S, we have n vectors u1, u2, un, and span of S by definition is the all possible linear combinations of the vectors present in capital S. Okay. Now you see, now if we consider the linear combinations in this manner, these scalar quantities has to be chosen from the field on which this V is a vector space, and according to the given question, the V, the field considered over here is Z2. Okay, so Z2, you already know from our previous example that Z2 is a field, a finite field with some operations, and it has only two elements in it, that is 0 and 1. So each of these scalar quantities can have only two choices, 0 and 1. So if we have two choices for A1, for each of these choices, the second scalar can be chosen in two ways. So the two scalars can be chosen in two ways, two into two ways, that is two squared ways. This is the fundamental rule of counting. If the first two scalars can be chosen in two square ways, for each of these choices, the third scalar can be chosen in another two ways. So the first three scalars can be chosen in two into two, that is two cube ways. And in this way, if we go up to n vectors, the total number of ways by which the scalars a1, a2, an can be chosen is 2 to the power n. And since span S contains the linear combination of all possible linear combination of the vectors, so linear combination is dependent upon the choice of the scalar quantities. And if the choice of the scalar quantities is 2 to the power n, so total number of vectors present in span S will be 2 to the power n. That is how we have got our answer. Now, for this example, let us try to find it out. I am selecting an example like, say, let us consider three vectors. Let us consider three vectors 1, 0, 0, 0, 1, 0, and 1, 1, 0 from R3. Okay, and you know that R3 is actually giving you the it is actually the three-dimensional space, the collection of all three-dimensional points, that is your R3. Now 1, 0, 0 point is lying over here, 0, 1, 0 is actually lying over here if we consider this to be y and this to be x and that to be z, and 1, 1, 0 means somewhere here. So this is a vector that is 0, 1, 0. Okay, so let us write it as 0, 1, 0. That is a vector which is 1, 0, 0. and that is a vector which is 1 1 0. Okay, so we have considered three vectors in three-dimensional space. Now we are selecting three scalars. Select three scalars A, B, C from R. Why am I selecting this from R? Since R3 is a vector space over R. R3 is a vector space over R. Okay, such that A into 1 0 0 plus B into 0 1 0 plus C into 1 1 0 is equal to 0 0 0, the origin of the, because origin is actually the zero vector of the three-dimensional space R3. So from this we are getting A 0 0 plus 0 B 0 plus C 0. Okay, and from this we can write A plus C, and this can be written as B plus C, and A plus C and B plus C, and the last one is 0 plus 0 plus 0, that is 0 will be equated to the zero vector 0 0 0. Okay, and therefore we get A plus C equal to 0 and B plus C equal to 0. Now you see in this equation there are three unknowns and two equations are there. I shouldn't write the word equation here. Just a minute. I should write the word system. In this system, there are three unknowns and two equations. Okay, and you will see that these equations cannot be solved. This equation cannot be solved. You can express the unknown A in terms of the unknown C as A equal to minus C, and you can also express the unknown B in terms of the unknown C as B equal to minus C. So the unknown C is actually having independent choice. The unknown C is actually having independent choice. Okay, so if you put C equal to 0, then your A will become 0 and your B will become 0. But if you put C something else, then say if you put C equal to 1, then A will become minus 1 and B will become minus 1. So you can put any value for C, and you can check that if I substitute all these values over here, then okay, then one more calculation you need to do is that if I name this equation to be 1 and if I name this equation to be 2, 1 minus 2 gives you A plus C minus B plus C, which is equal to 0, and from there I get A minus B equal to 0, which is actually A equal to B, gives you A equal to B. So here are two things are happening. A and B are same, and A and B are depending upon the choice of C. Now if the choice of C is 0, then all the scalars are 0. If the choice of C is non-zero, all scalars are non-zero, but their linear combination is 0. And therefore, so the vectors 1 0 0 0 1 0 0 1, sorry, what vectors what vectors I assumed. Let me check. 1 1 0 1 1 0. The vectors are linearly dependent, LD. Okay, but if you consider these vectors carefully, you will get to see that I cannot express this vector as multiple of the other vector, or I cannot express 1 0 0 as a multiple of 0 1 0 or 1 1 0. Okay, I cannot express 0 1 0 as a multiple of 1 0 0 or 1 1 0. I cannot express 1 1 0 as a multiple of 1 0 0 or 0 1 0. I cannot express this. You can observe it very well from the expressions of the vectors. Okay, and so this proves our theorem. This proves our not proves, actually this shows our result, which is given in the question, that in this three-dimensional space there may be 3 points whose linear combination is 0, with not all scalars are 0. These vectors are linearly dependent vector. One vector is dependent upon the other vector, but linearly, by linear dependence we mean that one vector can be expressed as a linear combination of other vectors, but I cannot say that one vector is multiple of any other vector individually. These vectors 1 1 0, these 3 vectors, they cannot be expressed individually as multiple of other vector like this, but we can consider this vector as a linear combination of other 2 vectors. We can express 1 0 0 as a linear combination. Say I can write it as m1 for some values of m1 and m2. I can write it as m1 0 1 0 plus m2 1 1 0, but I cannot write it as this individually. Okay, no, 1 0 0, someone has written, Dheeraj Kumar. Yeah, Dheeraj Kumar, you are Aniket has written, and Dheeraj Kumar has rightly answered. 1 0 0 0 1 0 0 0 1, this vector is linearly independent vectors, so this example will not count over here. So linearly independent. Dheeraj, you are right. This session is about to end. In the next session I am going to introduce the topic called basis and dimension. Okay, so let us wait for the next session to begin.